Have you ever wondered why a shattered glass never jumps back together? Why smoke spreads but never returns to the cigarette? Or why yesterday is easy to remember but tomorrow remains unknown? In this video, we are going to uncover one of the deepest truths about the universe. You will learn why the laws of physics allow broken things to fix themselves in theory but never in reality. Why time has a direction, and how life itself might actually help the universe move faster toward chaos. Before we begin, make sure to subscribe to the channel and click the bell icon so you don't miss more informative and fascinating videos that explore the hidden laws of our universe. Now let us start with a simple question that sounds almost like a joke but leads directly into one of the biggest mysteries in physics. Can a broken glass fix itself? According to the basic laws of physics, the answer is yes. In principle, every molecule inside a shattered glass could slowly slide back into its original position. Given enough time, the fragments could assemble themselves perfectly, lifting off the floor and forming the exact shape of the glass again. But does that ever happen? Of course not. And that is where the real story begins. We usually think of ourselves as heroes in a battle against chaos. We build houses, organize cities, write books, invent technology, and create order wherever we go. It feels as if life stands against the natural tendency of things to fall apart. But physics quietly tells a very different story. Life does not resist disorder. In fact, life accelerates it. A rock sitting on the ground slowly erodes over time. Wind and rain gradually break it down. The process is slow and simple, but a living organism behaves very differently. A living being eats, moves, thinks, breathes, grows, and reproduces. Every one of those actions rearranges matter and energy at an incredible speed. From the perspective of physics, you are not simply surviving in the universe, you are helping it change faster. Every breath you take, every movement you make, every thought in your mind is part of a much larger process. It is the universe finding quicker ways to spread energy and increase disorder. In other words, life might not be fighting chaos at all. Life might be one of the universe's most efficient tools for creating it. When you look at it from this angle, something fascinating appears. Stars form, galaxies collide, ecosystems grow, and intelligent beings emerge, not as accidents standing outside physics, but as natural consequences of it. These structures are incredibly good at transforming concentrated energy into scattered heat. So the real question becomes deeper than simply asking why life exists. Instead, we might ask why the universe seems to need life in order to complete its own process of change. To explore this idea, let us look at something simple and familiar. Imagine a fresh piece of white chalk. It is smooth, solid, and perfectly shaped. When you hold it in your hand, it appears stable and complete. The structure of the chalk is held together by tiny electric forces between atoms, forming a rigid arrangement of matter. Now suppose I drop that piece of chalk onto a hard floor. The moment it hits the ground, it snaps into several smaller pieces. Tiny particles of dust scatter across the surface. What was once a single solid object becomes a pile of fragments. Now imagine we simply leave it there. Imagine dropping a piece of chalk and watching it shatter. You wait a year and nothing changes. Now imagine waiting 10 million years. Will it rebuild itself? You know the answer, never. This is what physicists call the arrow of time, a one-way flow that defines our entire universe. At the atomic level, physics doesn't prefer a direction. The equations work perfectly forward or backward. So why does our world only move one way? The answer isn't in the atoms, it's in the counting. Imagine the air in this room. Trillions of molecules move and collide, spread evenly throughout the space. Is it possible for every molecule to suddenly gather in one corner? Physics says yes, but the odds are so low it simply never happens. There is no physical law that forbids air from suddenly clustering in one corner. Newton's laws don't prevent it. Probability does. Entropy is a measure of how many microscopic arrangements produce the same appearance. There are simply more ways to be messy than to be neat. When chalk breaks, there are countless ways for those pieces to scatter. The universe naturally moves toward these more probable disordered states. This is the second law of thermodynamics. The total entropy of a system tends to increase over time. The arrow of time emerges from probability itself. Imagine a box with black sand on one side and white on the other. Shaking it blurs that line. The original order disappears, not because of a force, but because of statistics. Eventually, the box becomes a uniform gray pile. The universe moves from states with fewer possibilities to states with many. Physics at this level isn't about forces, it's about possibilities. Once you count the ways things can happen, the mystery of disorder becomes clear. Now comes the important question. If we keep shaking the box for a very long time, thousands of shakes, millions of shakes, maybe even shaking it continuously for years, will the sand ever return to its original state? Will the black grains somehow gather themselves back on the left while the white grains return to the right? Your common sense says no, but remember, physicists do not rely on common sense. We rely on the rules of motion. According to the laws of physics, every grain of sand simply responds to forces and collisions. A grain does not know whether it is black or white. It does not know where it belongs. When it gets bumped, it moves. When it collides with another grain, it changes direction. There is no law that forbids the grains from separating again. In fact, if the box were shaken in exactly the right sequence of motions, each grain could move back to its original side. The laws of motion allow it. There is nothing physically impossible about the sand returning to perfect order. So why does it never happen? The answer is not hidden in physics, it is hidden in mathematics. Let us examine the mixed box more carefully. Suppose the sand is completely gray and mixed. Now imagine swapping the positions of two grains near the center, one black grain and one white grain. From your perspective outside the box, nothing has changed. The sand still looks gray. Now imagine swapping 1,000 grains from the left with 1,000 grains from the right. Once again, the box still looks gray. There are countless ways to rearrange the grains internally while keeping the overall appearance the same. These hidden internal arrangements are called microstates. A microstate describes the exact position of every grain inside the box, but many different microstates can produce the same visible result. In the mixed box, there are trillions upon trillions of possible microstates that all look like gray sand. Now compare that to the perfectly separated box we started with. Black on the left, white on the right. If you swap even one grain across the boundary, the arrangement is no longer perfectly separated. A tiny white speck appears on the black side. There are extremely few microstates that maintain perfect separation. So when we shake the box, we are not guiding the sand toward disorder. We are simply letting it move randomly from one microstate to another. Because there are vastly more mixed arrangements than separated ones, the system almost always ends up in the mixed state. This is the essence of entropy. Entropy is not simply disorder, although that word is often used. A more precise definition is this. Entropy measures the number of possible microstates that correspond to the same visible condition. Low entropy means there are only a few possible arrangements. High entropy means there are many. The separated sand has low entropy because there are very few ways to keep it separated. The mixed sand has high entropy because there are an enormous number of ways to keep it mixed. Now, the second law of thermodynamics becomes clearer. It does not say that disorder is forced upon the universe. It simply states that systems naturally evolve towards states with more possible arrangements. At the very beginning of the universe, entropy must have been extraordinarily low. The Big Bang, the event that began our cosmic history about 13.8 billion years ago, could not have been a chaotic explosion in the usual sense. If the universe had begun in a completely disordered state, there would be no direction for entropy to increase. Everything would already be maximally mixed and nothing interesting would ever happen. No galaxies would form. No stars would ignite. No planets would emerge. Life itself would never appear. Instead, the early universe must have started in an incredibly special condition, a state of extreme order and very low entropy. It was like a tightly wound spring or a clock that had just been wound up completely. Everything that happens today, the shining of the sun, the breaking of chalk, the beating of your heart, is part of the slow unwinding of that original state. The universe began organized, and ever since then it has been gradually exploring more and more possible arrangements. But here is where things become even more interesting. When most people imagine the Big Bang, they picture a violent explosion filled with chaos. Flames, debris, particles flying in every direction. Intuitively, that looks like a high entropy situation. Yet when physicists study the early universe, they discover something very different. Shortly after the Big Bang, the universe was remarkably smooth. Matter was spread out almost perfectly evenly across space. The density of matter in one region differed from another by only tiny fractions. At first glance, a smooth and uniform distribution might seem like a state of high entropy, similar to gas spreading evenly inside a container. But gravity changes the rules completely. Gravity has a unique property. It pulls matter together into clumps. Over time, gravity gathers gas into clouds. Clouds collapse into stars. Stars cluster into galaxies, and galaxies form massive cosmic structures. In a universe governed by gravity, the state of maximum entropy is not smoothness. The true high-entropy state is one in which matter collapses into extremely dense objects, especially black holes. In fact, black holes represent the highest entropy objects known in the universe. When we look back at the early universe and see that matter was distributed smoothly rather than already collapsed into countless black holes, we realize something extraordinary. The universe began in an incredibly unlikely state. It started in a configuration that was extraordinarily ordered compared with the many chaotic possibilities that could have existed. This idea is sometimes called the past hypothesis, the assumption that the universe began in a very special low entropy state. But this realization raises a deeper question. Why did the universe begin that way at all? Why did the cosmic sandbox start perfectly arranged instead of already mixed into chaos? To answer that question, physicists must look even deeper into the nature of gravity, space, and information itself. To understand just how unusual the beginning of the universe really was, we have to bring gravity into the picture more carefully. In everyday situations, like the sandbox of black and white grains, disorder means mixing. Sand spreads out, gases diffuse, and heat flows until everything becomes evenly distributed. But gravity changes the meaning of disorder in a dramatic way. In systems where gravity dominates, matter does not prefer to spread out forever. Instead, gravity pulls things together. Clouds of gas collapse under their own weight, forming stars. Stars gather into galaxies. Galaxies cluster into vast cosmic structures. If gravity were allowed to run its full course without interruption, the universe would not end as a thin, uniform gas. It would end as a collection of enormous black holes. Black holes are extraordinary objects where gravity is so strong that not even light can escape. But they also hold a secret. They represent the ultimate state of disorder, containing more entropy than anything else in the universe. In contrast, the early universe was incredibly smooth, a state of extraordinarily low entropy, like a ball perfectly balanced at the top of a hill. Gravity caused matter to clump, creating stars and galaxies. Each step in this process increases entropy, slowly unwinding the cosmic clock. Physicist Roger Penrose calculated the odds of our universe beginning in such a precise state at 1 in 10 to the power of 10 to the power of 123. That initial order is the source of everything today, from the sun's energy to the very thoughts in your brain. The Big Bang was a tightly wound clock. For 13.8 billion years it has been unwinding, and we are living right in the middle of it. Entropy is not just about disorder. It's deeply linked to information. Consider Maxwell's demon, a tiny creature sorting gas molecules to create order from chaos. This puzzle was only solved when scientists realized that storing and erasing information has a physical cost in energy. Information isn't abstract. It interacts with the thermodynamic laws that govern our entire universe. We see this most dramatically in black holes, which push the relationship between entropy and information to its limit. For decades, the black hole information paradox challenged physics. If information vanished inside, the universe's total entropy would decrease. But physicist Jacob Bekenstein proposed that black holes must possess their own entropy to compensate for what they absorb. This discovery preserved the laws of physics, revealing that even in the darkness of a black hole, information survives. But the story took an even more surprising turn when Stephen Hawking studied black holes using quantum mechanics. His calculations revealed something astonishing. Black holes are not perfectly black. They slowly emit radiation, a faint glow now known as Hawking radiation. Over extremely long periods of time, this radiation causes black holes to lose energy and gradually evaporate. This discovery meant that black holes behave like thermodynamic systems. They have temperature, they radiate energy, and most importantly, they possess entropy. In fact, the amount of entropy in a black hole is enormous. It is proportional not to its volume, but to the surface area of its event horizon. That detail led to the holographic principle. All the information inside a region of space may actually be encoded on its boundary surface. Just like a hologram, the universe itself might store information on its outer surfaces, while the world we experience emerges as a projection. The deep structure of reality appears to be built not only from matter and energy, but from information. And that brings us back to life. At first glance, living organisms seem to contradict the second law of thermodynamics. Life creates structure. DNA stores vast quantities of information. But life does not break the laws of physics. The key insight came from Erwin Schrödinger. He realized living organisms are not isolated systems. Living beings constantly exchange energy and matter with their surroundings. They maintain internal order by exporting disorder into the environment. You eat food, using its energy to build cells and power your brain, but in the process, your body releases heat and waste, increasing the total entropy. Life survives by accelerating the spread of entropy elsewhere. We are not rebels, we are participants in the universe's overall process. Stars release energy, planets redistribute it, we capture and transform it. We are part of the great flow from order toward disorder. The reason anything interesting happens, the reason thoughts form in our minds, is because the universe began in such an ordered state. One day, trillions of years from now, the stars will burn out. This is the heat death of the universe, but we are not living at the end. We are living during the unfolding of the process itself. Every falling leaf, every fading sunset is part of the same cosmic movement. The atoms have arranged themselves into us, beings capable of looking back at the universe and understanding its flow. We are the universe's way of understanding why broken things never put themselves back together. Thank you for watching.